right, hello everyone. So today we're gonna get started with. Oh, excuse me. Today we're gonna get started. Um, what's a good way to study for 2150 during the summer? So I haven't taught 2150 before, but what I would say is I believe the class is taught in C, so just learning a little bit about C probably wouldn't hurt. But at the same time, I don't have insider information about 2150 as I haven't taught it yet. And given that I've only been here, this is again only my first year. I'm still trying to figure out all the details of each class. My mic is super quiet. Well, let me fix that. There we go. Hey, it's probably better. Anyway, so today we're going to pick up with recursion. We're going to talk about divide and conquer strategies, specifically how those are used in recursion. From there, um, just some general announcements. So, of course, homework 5 is posted due Friday. That is due this Friday at 11:30. Do we have an in-class activity today? So officially the in-class activity for today was the in-class activity for Friday last week. So if you've already submitted that, then you're good to go. So this is due Friday 11:30, homework 5. Remember that only recursion is auto-graded. The rest of the assignment says on the PDF it's due Wednesday. I'm aware it says that, and I've asked the person who made the PDF to fix it. But where it says it's due Friday is on Colab and on WebCat, and actually WebCat's kind of the main issue. Is if the WebCat deadline were off, then we would have a problem. But the WebCat deadline is Friday at 11:30, so it's due Friday at 11:30. Only recursion is auto-graded. The rest of it graded manually. Correct. It is just for the recursion portion. Although I may need to check to see if it should actually be 50 points. I can't recall entirely. I'll look into it this afternoon, right after this class is over. But in the meantime, the graded manually portion includes the concurrency portion. So that relates to the threading stuff. The correct behavior is as follows for the threading. All 20 messages print. If you're only printing 16, it's incorrect. Second, and by the way, don't care about order. Let me resize the font here just super quickly. I don't care about the order. Just don't care because the order is unpredictable from threading. But additionally, program terminates. No threads hanging. By this I mean, when I run a program like I'm going to run today, you'll notice that when the program is done, how this stop button is grayed out. If this stop button is still red, it means there is some thread still running. If the thread is still running, you will lose points. So, these are the two requirements. The program must fully terminate. That means all threads, not just the main thread. Any other questions? And test grade ETA. So we have the exam almost fully graded, but I don't have an ETA because that's not something that I can act unilaterally on. I would be surprised if it were later than the end of this week. That is to say that I don't want to promise a particular day. All right. So with that, we are going to now take a step into, and if you'll excuse me for a second, I need to close some windows here. We're going to take a step into the slides for the day, and actually, I'm going to borrow them from Professor Bossett today, which we've gone over the slides, but I just want to, well, first let's take a minute and let's just refresh what we talked about last time in class. We talked about last time recursion, the idea of a self-referencing process. So building a solution by solving a simple problem and using kind of a nested nature of solutions to solve it. And we talked specifically about the Towers of Hanoi example. We talked about Fibonacci. We talked about recursion. Today, what I want to talk about is divide and conquer strategies. And we've actually already discussed the first version. We've already talked about, if I go to Eclipse, go to algorithms, we have already talked about binary search and how it is O of log n time, whereas a linear search, while simpler to code, is O of n time. Now, we have implemented this in an iterative way, but we can implement this process really in a recursive way just as well. And so in order to talk about how our recursion works, the first logical step in any recursion problem is to think about the base case. And my question to you is, and there's technically multiple answers, but I want to go with the simplest possible correct answer for this, which is, if I have, sorry, a cat just knocked my camera over. One second. If I have a list, or an array in this case, if I have an array, what qualities are going to make my array the easiest possible array to search? If I'm looking for some target, and I have some array of some size, which array or what setup is going to make this array the easiest to search? Target equals mid, order, well, hang on. So in this case, if we're talking about a binary search, we're going to already assume the array is sorted in ascending order. Because if it's not sorted in ascending order, there's no point even trying to do a binary search. You can't do a binary search at all correctly on something. Target equals mid. Well, I mean, that could work, but does that work is that the simplest array? Some may think, what if this array were size 1? What if I'm searching an array of size 1, only one element? This is pretty simple, right? If the length is 1, I only have one value to search. But can anyone think of anything simpler? Something even simpler to determine than this, whether or not a value is in an array. Length is 0, right? If my array is empty, and an array can be length 0, if my array is empty, this is my array. There's nothing there. This is a very simple array to search, right? What is the return value if my array is empty? If the size is 0? If I do a binary search, exactly, it's not null, it's -1. Because remember, when we are doing a binary search, we're returning an address as an integer. And we cannot return null because there is no integer value null. You cannot, in Java, say anything like int x equals null. This doesn't work. This line of code does not compile. So we use a sentinel value, and that sentinel value for not found is -1. So far we've implemented this in a iterative way. Let's take a minute and let's implement this, in an iterative way. And don't mind me, not that I was practicing lecture or anything. The first thing I'm actually going to do is this. I'm going to define my recursive function. In order for me to define my recursive function, remember, the idea is I have some array like this, and I want to divide and conquer. So I'm going to look at this value, and if I know that the value I'm looking for needs to be to the left, I'm going to ignore all of these. So the idea is I'm going to narrow down what I consider my low and my high, which is exactly how we did iteratively. And so because of this, I need to include in my recursive definition the values low and high. These are going to be the places in between, and this is inclusive, so including the low and including the high, where my values can possibly be. But the thing is, I don't want the user to have to call a binary search like, or I want the user to be able to call a binary search like this. They pass in the array and they pass in their target. I don't want them to have to know that low and high exist. I want to hide this from them because, simply put, they don't need to know it, and I want to make my program as easy to use as possible. So instead, I'm going to write a function that takes in an array and a target, but it's going to call a private helper function. So return binary search helper. This is going to take in the same array, the same target. What is my low value going to be? If I'm searching the entirety of array, what should my starting low value be? 0, right. The first index. Again, specifying that this is inclusive, what should my high value be? Specifying that high is inclusive. That means including the index high. Array.length minus 1, exactly. Array.length minus 1. Not array.length. If I weren't including high, I would say array.length. But in this case, array.length minus 1. Good. Now, my question was earlier, what array is the simplest to solve? And the answer was an array of length 0. Given this function definition, I am searching this array for target from low inclusive to high inclusive. What would be my base case if something returned -1? Because remember, this was what we returned in our base case. How would I define this base case? Because I can't say array.length equals 0, because I'm not actually changing the array. If high equals -1, no. Not if high equals -1, because high, well, 1 couldn't be, because it's there. If low equals high, well, no, because if low equals high, that means my array is length 1. Correct? Because remember, we said including on the low side low and high. If those values are equal, that means my array is length 1. So I can't say if low equals high. If low is greater than high, or high less than low, either or. Not if array equals null, because this array won't equal null. If array equals null, we're going to immediately just have another problem. We're not ever setting this array value to null in this recursive function. Remember, we don't want this function modifying the array. We only want to find a value. So this is our base case. And then our recursive step is just going to continually narrow down the search space. Now, technically in this case, we can early exit the recursion. But I wouldn't really call it a base case, what causes us to early exit the recursion. So, let's do else, and we're going to do int mid equals high plus low divided by 2. Nothing new here. Then, if array mid equals target. This is where we can early exit the recursion, but we wouldn't really call this a base case because it's not a simplest version of the problem to solve. This does mean, however, we found target. And so we return mid. Again, not really a base case because this isn't the simplest version of the problem. But it does lead to us exiting the recursion. Now let's do else. Let's do target is greater than array mid. Now if target is greater than array mid, this means we need to look right. Why does it not like this? Oh, else if, sorry. Else if. If I want to look to the right, what should I do? Yeah, correct. If I want to look to the right, what should I do? How would I do that? Low equals mid plus 1. Well, I could do that, but the problem is I don't have a loop. So if I say low equals mid plus 1, well, so do I need to then just rewrite all this code and nest it? Call the helper function again. Right, I'm going to recurse on the same helper function. And I'm going to recurse with the arguments array, because my array hasn't changed, target, because my target hasn't changed. What are my next two arguments? The array and the target haven't changed, but high and low may have. We have some people saying mid plus 1 high. Anyone think this is not correct? Again, I can't say low equals mid here because I don't have a loop. Right? I'm going to call the function. That function has separate local variables. And further, I wouldn't want to set low equal to mid. And the reason is that, remember, we're including low in our search. And we've already found that mid is not the solution. So there's no reason to check. There's no reason to check mid again. So this is actually correct. This is the correct recursive call. And now the second time we call this function, low will be equal to mid plus 1 the first time we called it. And then from there, yeah, we just return that output. Else, and it's going to be very similar again. But what are our arguments? Our first argument, second argument haven't changed. Low, comma, mid, minus 1. Exactly. So this is the recursive way. And if you look at this, you'll notice right out of the gate that this code, if I put them side by side, looks actually rather similar to the iterative solution. The difference is, instead of using a loop, which I need to add some extra white space down here just so I can match these up line for line. If you line these two up, you'll notice they look very similar. Very similar. The difference is we're using recursion rather than a loop. And so we can't just modify high and low like we did before. We have to actually recall the function with different arguments, as you see here. And technically I did this in the worst order, or in the opposite order. So on the left, I did look left first, and on the right, I did look right first. But this is a divide and conquer strategy. Any questions so far? Does recursion versus loop change the algorithm complexity? No, they are both O log n. Does it change the runtime? I mean, remember that runtime is subject to a lot of factors that the algorithm complexity isn't. So I'm certain it changes the runtime. If I had to guess, I would say it would be ever so slightly longer, but not dramatically so. And certainly not anything resembling an order complexity. They're both still O log n. Could base case also be if high equals -1? No, because the problem is high might never be -1. The problem with that is, let's say I searched. So here I have an example where I'm searching the array for value 19. The problem here is I would first search 23. I would look left. So I would be recursing from 0 to 2. I would then get my mid as 15. And I would look right, so I would be searching from 2 to 2. High would never be -1 here. So this wouldn't work. So it has to be very specifically the relationship from low to high. It has to be that. We can't assume that high will approach -1 because it won't. In this case, the program will end when high is equal to +1, not -1. Will code be posted on Colab? Yeah. As always, it will be. All right. So now, let's take a minute. I wanna do a quick little example of something. Let's say that you're at work and your boss hands you a stack of papers. Your boss hands you a stack of papers, 16 of them, and tells you to sort them in ascending order. Now, let's say you use a sort that we're familiar with, something like a selection sort. If we have a selection sort, well, in order to find the minimum of 16 values, we first have to do 15 comparisons. That finds our minimum. We have one value sorted. Then we need to do 14 comparisons over the remaining values to give us the second value sorted. Then 13, then 12, ... all the way down to comparing two values and then the last value. So this series is the summation of 1 to 15. And if you're not familiar, there's a classic story. There's a mathematician, Gauss. Gauss, when he was a kid, the teacher wanted to give the students busy work. I guess they were hungover or something and didn't want to actually have to teach that day. So they said, okay, every student add every number from 1 to 100. And most of the students started immediately thinking, okay, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. Gauss immediately raised his hand and said the correct answer, which was 5,050. How did Gauss do this? Well, write out the summation series. And let's just write the first few values. ... 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. 4 plus 97 is 101. Oh, hey, look, they're all 101. There's 50 ways to get to 101. This equals 5,050. That's how you do it. This summation, now let's break it down. This value is half of n, so 1/2 of n. And this 101 is equal to n plus 1. So the sum of every value from 1 to n is half of n times n plus 1, which equals n squared plus n over 2. This is big O n squared. So I'm going to say to do a selection sort on n values, keep in mind that our n in this case is not 16, it's 15. So I'm going to replace the n here with n minus 1. And if I replace the n with n minus 1, what this means is our actual number of steps. Give me 1 sec. Yeah, merge sort alert. You're exactly on the right track. So, our number of steps for a selection sort. And the reason I picked selection is because insertion, it's a bit murkier. It's more probabilistic. Number of steps for a selection sort. If I replace this with n minus 1, all this does is this changes this term to n minus 1 times n. That means this is n squared minus n over 2. So if this is my formula, let's say that you did a selection sort, again, using n as 15, that is 1 less than the number of papers you need to sort. To this end, I'm sorry, I'm just occasionally stepping up to read in case there's questions. To this end, let's use this formula. How many steps will it take? Well, 15 squared is, I believe, 225. Minus 15 over 2, that's going to equal 2100 over 2. That's going to equal 105. So it's going to take you 105 steps to sort this with a selection sort by yourself. But let's say you don't work in this office alone. Let's say you work with someone else. And what we're going to do is rather than you sorting all this work by yourself, we're going to have you break this up into 2 stacks of 8. And you're going to hand this stack to a friend, and they're going to help you. Let's see how many steps this now takes, combined, total, between both of you. Well, sorting a stack of 8 requires 7 plus 6 plus ... plus 1 steps, and you have to do it twice, correct? So 2 times this. Plug this into our formula down here. N is 7. If n is 7, this is 49 minus 7 over 2, which equals 42 over 2, which equals 21. So 2 times 21. That takes 42 steps. But then we have to do something else, because we're not done. Now we have 2 separate stacks of sorted papers, right? So now what we need to do is, let's think of it like this. We have 2 stacks of papers, and these are sorted in some order. And what we're going to do is we're just only going to look at the top piece of paper. And whichever is, and in this case, this is sorted the smallest last name, or sorted alphabetically with A at the top. Whichever of these comes first alphabetically, we're going to remove it from the stack and put it into this list in order. So I remove this value, I put it in. I remove this value, I put it in. However many comparisons I do, the most comparisons I would have to do, remember these stacks are size 8, is I'd have to compare total 15 times. And the reason is, once I'd be left with 1 sheet of paper, there's nothing to compare it to. So it takes 15 steps to, and this is, by the way, called a merge, to merge these 2 stacks of paper, plus 15. After that, the whole set of 16 is sorted. You add this up, 57. Holy cow, look how much faster that was. Just by breaking the problem in half and merging it, I mean, we've saved almost half the time. Again, we haven't done anything yet with recursion here. All I've done is, instead of sorting a list of 16, I sorted 2 lists of 8 and merged them. And wow, this saved so much time. Let's try this again. Again, so far our numbers we have 105 and we have 57, right? Let's now try again. Let's take this one step further. Rather than sorting 2 sets of 8, let's now say we break this up even further. Let's say we sort 4 sets of 4. We merge those 4 back into sets of 8, and then we merge those 8 back into sets of 16. Well, 4 plus 3 plus 2 plus 1, that's just 10. And we have to do this 4 times, right? So 40. 40 steps to sort these values. Well, now we need to merge these back. How many steps is it going to take? It's going to take 7 and 7. Did I do something wrong with the math last time? I think I had to have done something wrong with the math. That number can't actually be 57. Did I forget to carry a 1? Hang on. 7 plus 6, 7 plus 1 is 8. So it's going to be 20. Did I say 21? It's actually going to be 28. So it was, I did say 21. So add 14 to that. Sorry, I lied. This is actually 71, not 57. I did do a math hiccup, and no one in chat caught me, and I'm disappointed. Anyway. Sorry, the previous step was actually 71 because I accidentally left 14 off the sorting. Anyway. So now, 4 plus 3 plus 2 plus 1 is 10. We do that 4 times. We have 40. We then merge. Each of these merges takes 7. So 2 times 7, that's plus 14. That gives us 54. Then we merge these two stacks of 8. Once again, this takes 15 steps. This takes 69. 69 is actually still less than 71. Let's break this up even more. Again, I'm just doing selection sort here. 2, 2, 2, 2, 2, 2, and 2, and 2. Now, if I want to, and actually, by the way, I was wrong here. Sorry, it should be 3. So this should actually be, sorry, another math hiccup. This should be 6. So that's 4 less times 4. That would actually be 16 less. This would be 53. Sorry, another math hiccup. I'm doing the best I can. Apologies. Not a math teacher, damn it. I'm a computer science teacher. Anyway. So from here, how many steps does it take to sort two values? Well, it just takes one, right? They're either in order or they're out of order, correct? So that's one step, 1, 1, 1, 1, 1, 1, and 1. So that's 8 steps. Then from there, I need to perform the merge. At most, this takes 3 steps. Each of these takes 3. So that's plus 12, that's 20. At most, each of these takes 7, so that's plus 14, that's 34. And at most, this takes 15, that's going to be 49, which is still even less. All I'm doing here is breaking the problem up into smaller and smaller pieces. And by doing so, I have arrived at a runtime that is significantly shorter. And that idea is the basis of the merge sort. The merge sort defines a base case as sorting an array of size 1. Because we can't sort an array of size 0, there's nothing to sort. And sorting does require having something. So we can't sort an array of size 0, but we can sort an array of size 1. Here is an array of size 1, and I'm going to sort it. All right, I want you all to watch really close. I'm going to sort it. Ready? All right, and I'm done. All right, everyone see that? Here, I'll do it again real quick. All right, I'm done. Good. There we go. It's sorted. It doesn't take any steps. And so what we are going to do is we are going to break our array down into smaller and smaller sizes, and then we're going to just merge them. And in fact, the idea of the merge sort is the sorting only happens when we merge. That's the basis. And by the way, the merge sort code is already uploaded. You can look at it right now. It is on the algorithms day. And here is the merge sort. Again, we have our base function. This does create a temporary array, and we'll talk about how that works in a second. But then we just call merge sort from 0 to length minus 1. That is sort from low to high inclusive. We then say, okay, the base case is left less than right. The base case is actually left equals right. If notice that all of our code is in here. This would be the same as saying if left greater than or equal to right, return, and then just saying else here. This does the same thing. But since we're just returning, and with sorting, we return a void because we're modifying the array in place, same as we did before. Since I don't really need this, we're just going to write it this way. So the base case is when left and right are equal. So how are they defined? That's a great question. So first, before I get any further, let's actually animate the list sort. Or the merge sort, excuse me. Let's animate the merge sort. So I'm going to create some numbers let's say, and I'm not going to put these in order. Let's say 1, 2, 3, 4, 5, 6, 7, 8. 8, 6, 7, 5, 3, 0, 9. And let's just put a 4 over here. And I'm actually going to change 7 and 5. Sorry for you 80s fans out there. Question. That was announced earlier. If someone could just type that for me. All right. So from there, I'm going to break this array in half. Now first, up here, my left equals 0, and my right equals 7. My left is 0, and my right is 7. From there, I'm going to define my center. My center is the average of these two numbers, so it's 3. I'm going to go recurse on left to center, 0 to 3, as well as center plus 1 to right, so 4 to 7. So think of this as separating out this array. This is 8, 6, 5, 7. This is 3, 0, 9, 4. Now from there, I check my condition. Again, this is, and I'm going to abbreviate left to L and right to R. 0 to 3, this is not my base case. Left and right are not equal. Right is not less than left. So we don't do anything. Here I have right is 4, or excuse me, left is 4, right is 7. So I need to break these up even further. So I'm going to break them in half again. 8, 6. 5, 7. 3, 0. 9, 4. In this case, my left is 0, my right is 1. My left is 2, my right is 3. My left is 4, my right is 5. My left is 6, my right is 7. But I still don't stop. I still break this up even further. 8, 6, 5, 7, 3, 2, 9, and 4. From there, let's look at my left and right values. My left is 0, my right is 0. 1 and 1. 2 and 2, 3 and 3, 4 and 4. Or sorry, 4 and 4. This one's 5, 5 and 5. 6 and 6, 7 and 7. And you may be thinking, what if the size of my array is not a power of 2? This approach would still work. Why did 0 become a... why did 0 become a 2? Because my handwriting is so terrible that I thought I wrote a 2. That's why. It's a 0. I fixed it. My handwriting is just garbage. We have now actually finished the recursion here, and now all we need to do is merge back up. Are the comparisons happening concurrently? Not by default. You would have to add threading. By the way, I'm dealing with a storm right now, although it doesn't look like it's storming at the moment. But if all of a sudden the stream cuts out, just assume I lost power. So from here, I now perform the merging. So let's take a look real quick at the code. Everything I've done up until now is recursing on these two calls of merge sort. And technically I haven't actually hit the right branch yet, but for now I've been recursing on these two calls. Now I perform the merge code, and the merge code looks kind of scary, but we're just going to walk through it. It turns out to be fairly simple once you map it out. It just takes a little bit of extra language to formalize it into code. So now let's talk about how we're going to do this merge. I'm going to put this code up here, but I'm going to go back to the whiteboard. So for now, what I'm going to do is I'm going to cheat a little bit. Actually, this is not cheating. This is what the code does. In order to help my sorting, I'm going to, down here at the bottom, create a temporary array. A temporary array of the same size as my main array. So this is temp. And what I'm going to do is I'm going to use this kind of as a sorting space. And I'm going to copy sorted values back up. So the first thing I'm going to do is I need to sort these two arrays. And they go from value 0 to value 1. And I need to sort 8 and 6. And the way I'm going to do this, I'm going to look at the two values. I'm going to say, okay, which comes first? And if we're sorting in ascending order, 6 comes first. At this point, I have now used 6. So I can't consider it again. My only value left is 8. So I'm going to copy 8. Then from there, I'm going to copy this temp array back up into my permanent array. Now, I could write it up here, but the point is, I'm still sorting this same array here. This step actually isn't done until the merge is done below it. So really, I can copy these values back up to here. Just understand that this is all the same array. Everything in purple is the same array. So technically, changing 6 and 8 here is the same as changing 6 and 8 here because it's not different arrays. It's the same array. But I just want you to realize that I'm effectively copying it back to the array. I'm not always going to change it everywhere. I'm just going to change it down there. But the point is, this is all one array again. So I'm going to use blue for my temporary array, purple for my main array, the array I'm actually sorting, the variable A in my code. And again, this code is already uploaded. You can find it under sorting examples. Sammy, I did actually answer that question. Again, unless you add threading, this won't happen at the same time. So by default, no. I do have, and I actually have already uploaded, a concurrent merge sort, which you can take a look at how that's done. So now I need to merge 5 and 7. I'm going to merge them. They go from 2 to 3. So from index 2 to 3 of my temporary array. And by the way, I'm just going to overwrite values on my temporary array. I don't really care much. From 2 to 3, okay, so which comes first, 5 or 7? 5 comes first. Then 7's left over. We come over here, 3 and 0. This goes from 4 to 5. Which comes first? 0. Then 3. Which comes first? 6 or 4? 9 or 4? 4, then 9. Again, from 6 to 7. And again, as I do this sorting, I copy these values up here. So this becomes 5 and 7. It hasn't changed. This one, 0 and 3, changes this array. 0 and 3. And then 4 and 9 changes this array. So I've done my lowest level merges. But now I need to merge these two arrays, 6, 8, and 5, 7. So how am I going to do this? Well, I'm going to do the same approach, except now instead of only one value, I have 2 to consider. So I'm going to only look at the leftmost value in each subarray. And I'm going to say, okay, which is smaller, 5 or 6? And 5 is smaller. So remember, this goes from index 0 to 3. I'm going to overwrite my temporary array from 0 to 3. I'm overwriting these 4 values. So which is smaller, 5 or 6? It's 5. So I'm going to put 5 here. At this point, I have used 5, so I can't use it again. And I'm going to, instead of looking at 5, I'm going to look at the next value here. Now I'm comparing 6 to 7, which is smaller, 6. So I erase this value, overwrite it with 6. I've used 6 now, so I increment this pointer. From there, I compare 7 to 8. 7 is smaller. I overwrite this value with 7. I've used 7. This leaves me only with the value 8 left. 5, 6, 7, 8. From there, I copy these values back up into the main array. So I copy 5, 6, 7, 8. And again, these two arrays are the same, so this would also be 5, 6, 7, 8. I just, for the sake of time, I'm not going to draw it. We do the same over here. We compare 0 to 4, and we're going to copy from 4 to 7. 0 to 4, 0 is smaller, so we copy 0 here. It's already there, so we don't need to change it. Then we compare 3 to 4. 3 is smaller, so we're done. And now we've completely exhausted the left list, or left array, but our right array is still here, so we just copy the values down in order. 4, then 9. I'm taking advantage of the fact that I know these sublists are in ascending order. I'm then going to copy this array back up to my main array. So this becomes 0. Excuse me, let me use the correct color. 0, 3, 4, and 9. My last step is to merge these two into the center array. And again, these arrays are the same. So let me just go ahead and make sure that this array is in a state that matches down here. Because these three arrays are all technically the same array. 5, 6, 7, 8, 0, 3, 4, and 9. So now to do my merge sort, I'm going to merge everything on the left half and the right half into my temporary array. So I compare 5 and 0. 0 is smaller. So this becomes 0. And I've used 0. Now I compare 5 and 3. 3 is smaller. This becomes 3. And I've used 3. 5 to 4. 4 is smaller. So I put 4 here. And I've used 4. Now 5 to 9. 5 is smaller. Put 5 here. 6 to 9. 6 is smaller. Sorry, I've used 5. I've used 6. 7 to 9. 7 is smaller. 8 to 9, 8 is smaller. And hey, look, my temporary array is now sorted because 9 would go in the last spot. I now copy this back up to the top. 0, 3, 4, 5, 6, 7, and 8. And I am now sorted. So that is the nature of the merge sort. Why do you use a temporary array? The reason I use a temporary array is because I can copy values into the temporary array without overwriting values in the main array. So the temporary array is kind of just like if you're sorting objects, it's kind of a shelf that you can use to sort them safely. Because remember, with arrays, if you change a value, that is destructive. That value could be lost. So we use the temporary array as just a place to dump things. So that is the merge sort. If you're confused, we'd be happy to help in office hours or reading, or you can go back and look over the material, look over the code, etc. I can't redo the example for the sake of time. What I am now going to do is I'm going to take one step and say, okay, so how do we end up with a runtime estimate of merge sort? And this is the key. Now, for the sake of time, I'm going to cheat. I'm going to say we're only looking at the number of comparisons. Only the number of comparisons. How many comparisons do we do going from array lists or arrays of size 1 to arrays of size 2? Well, we do one comparison between these two, one between these two, one between these two. So we do 4 comparisons. So 4. I'm going to, by the way, say that 4 is less than 8. So 4 is less than 8. From there, I'm merging these two arrays. This takes at most 3 comparisons. I do that twice. 3 plus 3 is 6. This is also less than 8. My last merge, I'm merging these two arrays. This takes at most 7 comparisons. 7 is less than 8. I have 3 rows that all take less than n time. So I could say this is 3n. But 3 depends on the size of my array. the number of times you can split an array in half is equal to the log n of that number. So if I have an array of size 1 million, log n would be 20, so it would be 20 times 1 million. So an overestimate of the number of steps the merge sort takes is n times log n, because we have log n rows, and the number of comparisons on each row is less than n. And the number of copies are equal to n, so technically you would say less than 2n, but point being, that still makes this n log n in terms of runtime. O of n log n. And you may be thinking, well, is there a sort that's better? And in terms of complexity classes, there is no sort that is better than O of n log n. Now, there is a sort that typically is faster, that is, it has smaller constants, and that is called a quicksort. But that sort is actually probabilistic in a absolute, although astronomically rare, worst case. A quicksort is equal to O of n, or is O of n squared in an astronomically rare case, but it can happen. So now some of you may be thinking, okay, I'm confused. Can you go through that merge sort again? And unfortunately, I can't go through the animation again. But what I can do is say, you know what really helps me understand things? I think what really helps me understand things is when someone illustrates sorting algorithms through the art of Central European dance. Traditional folk dance, of course, not modern techno-European dance, not that. But I find that traditional European folk dance really speaks to me in a way that nothing else does. And so to that end, this is the merge sort. And I will, by the way, link this video in chat real quick. And for the sake of time, I'm going to speed this up so it's going to look a little silly. So we have our array that we're sorting. We split it, and then we split each in half, and now we sort the left. We split the left half, and now we remerge the left. So I should note the order I did things on a merge sort actually wasn't explicitly correct. But you can see the front of the stage is being used as that temporary array. It's where we're copying values for the sake of temporarily sorting them before we copy them back to the main array. So A is the permanent array, B is the temporary array. Now we're seeing the merge of A2 with A34. Now we're going to see the merge, and I'll pause it here real quick. We're going to see the merge of these two on the left, A0 to A1, and these three on the right, A2 to A4. So we're going to compare A1 to A2. A2 is smaller. We'll compare A0 to A3. A0 is smaller. A1 to A3. And then there's nothing else to compare to, so A3 and A4 copy down. Now we're going to sort the right half. Of course, we have to do the little twirls. Very important. Don't forget to do that in your code. Obviously, that is not in code. This group, by the way, is called the algorithmics. I think I've talked about them before. Now we're splitting the right. We're going to make sure they're already in order. Copy them back. Now we merge A7 with A8 through 9. Now we merge A5 and 6 through A7 through 9. And now the last step, we're going to merge the left half of the array with the right half. And flourish. And again, I'm watching this at double the usual speed. They normally are not moving this quickly. So, with that, so that is divide and conquer. That is specifically divide and conquer as applied to a merge sort. So from there, that's going to be class for today. How many times does the array get cut in half? It depends on the size of the array, but as many times as it takes to get down to arrays of size 1, which that number is log n. So if I have a value, or if I have an array of size 1 million, it takes 20 cuts in half to get down to arrays of size 1. So with that, yeah. Actually, I am pretty sure that's actually what the group was. It was just a group of computer science students who also happened to be in a dance group together, and I think that's what led them to create that. Like a lot of my friends and I did swing dancing in college. So there were a lot of us in engineering who also did swing dance. I mean, it's just we didn't come up with anything as clever as that. So maybe that's my problem. Anyway, from there, we're gonna wrap up class for today. We will pick up Wednesday with linked lists, which is a recursive data structure. So we'll pick up on Wednesday with that. I will see everyone then. Hang on. There's Colby Bear. Yeah, the in-class activity is the in-class from Friday. And this is Colby Bear. Aww. And yes, his name is Colbert. My cats are named Stuart and Colbert. Is that a Guitar Hero in the back? There's a guitar. Oh yeah, no, I do have a Guitar Hero guitar. Yeah, I forgot about that. I forgot I have that. I played it a lot, and I've probably had it with me since undergrad, and I probably haven't plugged it in 10 years, at least 8. Um, I actually I started learning how to play guitar 10 years ago, so I haven't really played Guitar Hero since. Anyway, all right, that's all, everyone. Take care.